Good morning. I'm a PhD student from University of Seoul. I'm going to talk about how the halo motion and their mass evolution around the filamentary structures today. So as many people are talking about, the environment of galaxies is not static. So as it travels long distances, and they are co-evolve with the Okay. Closer to. Okay, maybe I could just. Can I did the COVID test. Yeah. So therefore, it could be important to consider their evolution in time series, as Oman et al. And some later works have done. They showed that halos, as they approach the clusters, occupy a specific region in the phase space composed of distance to the cluster center and the velocities. And not ignorable parts of these halos that have involved into the clusters must have come from the other types of cosmological structures, such as filaments, and they have suffered some type of transformation. So we call this pre-process, and I can summarize my presentation today is like this. Let's do the phase space analysis in time series on halos crossing the filaments. In order to do that, I think I have to first elaborate on how I did my calculation. So first is the data set. So I used the N-cluster run data run at Kavli. This is a dark matter N-body simulation data with cosmology of Planck 2016. And the details are on the table, so you can see it. And in the data, I found halos using Omega Halo Finder, and the resulted halo mass function is like this. So I didn't use all data. I cut the mascots to use to make the Galaxy Halo data and also the cluster-like halos. Cluster-like halos are those halos with mass over 10 to the 14 solar mass, and around the cluster center, I ran disperse on the dark matter particles around these cluster centers to find the filamentary structures. So especially this region. So I got the halo data and filament data, and what I did next is to calculate the perpendicular direction from the halo to the filaments to construct the full phase space diagrams. But it's actually not easy for the filament case, unlike in the cluster case, because in cluster case they can be approximated as sphere or a point, but the filaments is not a sphere. It's a one-dimensional long structure, so it was quite hard to construct the perpendicular direction. So we made some assumptions, some simplifications. There are two simplifications. The first is that filaments are straight line. So these black dots if the black dots are the filament structures I found, then I just draw a tangential line from a certain point to find a more clearer filament structures. And the second assumption is that filamentary structures are not moving so much. With this calculation, you can see the three representative case of phase space diagrams. So especially, basically there are two sets of halos. The first group is crossers and the other group is a non-crosser. So crossers are marked as green lines. These crossers are crossing the pericenter around the filaments where the perpendicular velocity goes zero. And some of these crossers would also pass the apocenter around the filament and go pass again another pericenter again, and some halos would just escape from the filament potential. And there are also non-crossers, which are marked as brown dot dash line, and they are actually not our main interest in our work. So now we got the phase space diagrams, and next we did is to define some parameters to identify each of the halo phase space trajectories, and you can compare this table to the top schematic one. So the R0 and V0 is the initial point in the phase space of halo, and the Vmax is the maximum perpendicular velocity a halo can get when they are approaching to the filaments. And they are T-formed. This is basically just an age of the filaments, I mean the halo. And we will constantly talking about the FC. These are first crossing. So I told you earlier that some halos are passing the pericenter several times, but we are only focusing on the first crossing moments. So RFC is the distance to the filaments when they are first at their first crossing moment, and TFC is just time since interval. I mean, time since crossing. And to see if there is any linear relationship between those parameters, we calculated Pearson correlation coefficients to find out that there are strongest correlation between the R0 and Vmax. This is partly because of our selection, because we are not considering the non-crossers, so the halos that are formed farther from the filaments with lower velocities would not be counted as crossers. So this is partly because of the selection effects, but also there are other reason too, which is that inner shells of the voids, which is where far from the filaments, they are more accelerated outwards towards the filaments, according to the previous research. So we can investigate more about this R0 and Vmax relation. So the first figure is colored by halo mass at current epoch, redshift 0, and the second panel is colored by T-formed, which is age. So in these two plots, we can conclude that massive halos tend to form earlier and have lower velocities for a given R0. So this is this can further imply that the density field at their formation time was not grown much, and they may have grown with the cosmological structure densities too. These halos are. Secondly, we plotted the phase space diagrams not in the full track, but at the fixed redshift, which is redshift 0 in this case. And we binned the halos according to their time since crossing. In this, and we also colored them by time since first crossing too. And in this plot, you can see the clear color gradients are shown from the recent crossers to first and second intermediate crossers. But at the last panel, which are ancient crossers, you cannot see the color gradients now. So this phase mixing, we call it viralization of halos around the filaments. What's more interesting is that this viralization pattern is quite similar to the ones from the halos around the clusters. The top work is by Oman et al. In 2013. They showed that when halos are viralized inside the clusters, they occupy a somewhat triangular region in the phase space, and the filament halos are showing the similar pattern in the phase space. So we call these viralized halos bound halos because they are bound to the filament potential. And these these halos we're still showing the color gradients. They are flybys. And in these slides, we are showing the differences of parameters defining the base space diagrams between these flybys and bound halos. So what you can see here, so let me summarize in these about these 6 figures that's here. So flybys are more likely to be ancient crossers. You can see here, ancient crossers, and they are formed farther from the filaments. You can see here. And because we already seen the R0 and Vmax relationship, we can also say that they have higher velocities. The flybys are having higher velocities. And in the last panel, we can show the flybys are more in the lower dense environments. But if you see the first panel here, this is the mass accretion distribution after the first inflow. So this quantity is how much mass a halo has lost or gained after the first inflow. But if you see this distribution, you might notice that flybys are almost always getting their masses after their first inflow, but bounds can gain mass or lose mass after the first inflow. So it could be, so this mass evolution is the mass evolution of bound halos are determined by other parameters. So we investigated mass evolution of halos. I'm first showing the same figure of this first panel, but as a function of time since first crossing. We internally call these plot banana plots because it looks like banana. If you see the 5 panel, can you see? I'm not sure if you can see the number here. So on the 5 panel, which are ancient crossers, they are not relevant to the colors. These colors are now 3D accelerations at crossing moments, and the halos in the 5 panel, they are not relevant to the colors. So these 3D accelerations could be highly relevant to the filament density, environmental density, but it's not showing the relevance. So it means the halo mass at this 5th region is not having the information on the first crossing moments and also the filaments. So we are looking at the recent crossers and intermediate crossers. So let's first see the mass evolution history of the recent crossers. You can see that if we subsample the halos in these recent crossers according to their environmental density, filament density, you can see that higher halos in the higher density environment are severely losing their masses after the first inflow, while halos in the low density environments are not. This similar trend can be seen in this intermediate crosser beans. In this panel, we are not calculating the filament density because we are estimating the density at redshift 0, and this is too long ago. So we instead measured the number of orbits around the filaments. Okay. We can assume that if the number of orbits around the filaments is high, then we can roughly say that this halo is around the high dense filaments. And you can also see that these red lines, which are orbiting around the filaments very many times, they are losing severe mass after the first crossing. Okay, so lastly, we also studied about mass segregation, which is the observationally confirmed phenomenon that massive objects are closer to the structural bones. We also see the mass segregation pattern in our simulation data, as in the first figure there. And a various type of reasons could be maybe in your head right now. The first thing would be a Kaiser bias. Maybe massive halos have formed closer to the filaments, but we have seen that the Kaiser bias is not the main reason of this mass segregation. So the second thing we thought of is maybe these massive halos have more time to sink into the cluster because, filaments, because they have arrived the filaments earlier. So we calculated the access time, which is the access time after they reach the 2 megaparsec from the filament spine. And we actually saw that massive halos have more time, had more time after they reached the filaments. To confirm this pattern, we also investigated the mass segregation pattern as a function of redshift, function of time. So we quantified the mass segregation as a massive halo fraction compared to the less massive halos inside 2 megaparsec from the filaments. And if you can see here, these green dots are universe average, and these black dots are the massive fractions inside the filaments. And you can see that the massive halos are always more around the filaments. But you can also see that this trend, this increasing trend, ends at redshift 1, and the decreasing trend starts. To determine why this is happening, we conducted 2 tests. First is that maybe, as this figure is indicating, massive halos are arriving the filaments earlier. That's the first case. And the second case is that, as we saw earlier too, the filaments are stripping the halo's mass. So that would be contribute to the weakening of the mass segregation trend. When we did the 2 tests here, the first one, which is that massive halos are arriving to the filaments earlier, is very well canceling the weakening of the mass segregation. So we can say that mass segregation is the cause, is the result of the massive halos approaching to the filaments earlier, and then less massive halos are approaching later. And lastly, what you can also think of is the dynamical friction, because dynamical friction works on massive halos more efficiently. They are losing their orbital energies around the filaments and can be sink in. But if you think of the dynamical friction, we should only care about crossers, because non-crossers have not reached the filaments at all. So we did this calculation with only crossers, and if you see, when you see these plots, you can see that without the differences in Vmax, velocities, and time distributions, only the displacement distribution is different in mass bins. The most massive bins are only the suppressed one in this distribution. So it means for crossers, there are dynamical friction working on it. So dynamical friction will partly is supporting the mass segregation trend. Yeah. So this is the end of my presentation. Thank you.
Thank you very much. Any questions?
Thank you for your wonderful work. It's fascinating to note that the mass segregation effect dwindles at the onset of cosmological acceleration. You showed this mass segregation effect as a functional redshift in this figure, and that dwindles at the onset of redshift up 1 something, right?
Yeah, right.
And that's the onset of the acceleration, right? So do you have any comment on the possible effect of dark energy cosmological constant on this dwindling of the effect?
Dark energy contribution
Yes.
of this. Oh, well, actually, I've never considered about the.
Well, it's very interesting to see that, right?
Yeah, right.
And I believe this mass threshold depends on the scale of filaments. So you should check its dependence on the scale of filaments.
Yeah.
Okay, thank you.
Thank you for the comment.
Question from Corentin still? Yes.
Very nice work. Can you go back to your banana plot? Because maybe I missed it, but most of the trends, the upgoing trends to the top right, is surely just due to the fact that if you wait long enough, halos will grow in mass. So did you remove, or do you have a way of like removing just the mean effects that halos grow in mass from this plot to see whether you still see a signal?
So why did I remove this in the discussion?
No, it's just if I take any halo whatsoever and I wait for 10 billion years, sorry, I can expect that its mass is going to grow by a factor of a few, which is what you're going here with the banana going up, right?
Yeah.
So have you tried removing the trends that is just due to the fact that halos grow in mass to see whether halos that have cross filaments have a different mass assembly history compared to halos that did not?
I'm sorry, but could you do a little bit slower? Sorry.
Yeah, sorry. So halos grow in mass, any halo. So you always expect that if you wait long enough, the mass at a given time divided by the mass they had is going to be larger than 1. So is there a distinct signature of the halos that have crossed filaments compared to halos that have not in terms of their mass assembly history?
So sorry.
Any other
Maybe we
questions?
could discuss after the session. Sorry.
Yes.
Yeah.
Absolutely. Any other questions? Super. Make me run.
I have a question about the simulation you are using. It's a dark matter only simulation, right?
Right.
So you are seeing how galaxies will feel the impact of the dark matter distribution in the form of filaments. So I can believe that galaxies actually feel the impact of the M structure. But at the same time, if you had a hydro simulation instead of DM simulation, then you would have more abundant gas supply near the filament. So there will be a positive effect of gas accretion as well as negative effect of the environmental effect. Can you have any comment on that, please?
Well, including the hydro simulation gas accretion. Hydro part would be our next work, our next project. So, yeah.
Other questions? So I have a simple question. I'm trying to relate your talk to Ulrika and Charlotte's talk. So Ulrika started off her talk by telling us that the satellites falling in, the galaxies falling in, they already lose some mass at the accretion shock, and then even more at the virial shock. And I was curious, where exactly do you think about, how far away from the central galaxy are you doing this analysis, or is it irrelevant?
Yeah, we are only considering the central galaxies. I'm not sure if you're asking this. The satellite galaxies are not considered right now.
Okay.
Yeah, we all removed it.
Okay.
Yeah.
And then maybe you could just elaborate how precisely, how confident are you about these distance measurements from the filaments, right? Can you really, is that a robust measurement?
Yeah, that is actually a hard question because we included a very strong assumption on the filament that it is a straight line and it's not moving. So let me show you this one first. Maybe this could be partly on your answer on your questions. So this is the original phase space diagrams, and this is the corrected one. What I corrected is to consider the what I did is consider the filament moving. So because filaments are moving, and we didn't consider it, our measure on the perpendicular velocities and also the distance to filaments would be, there would be an error. But if we tested it with the measuring of the filament velocities too, we get some slightly different phase space diagrams in here, but they are more compressed in distance, and they are more they're having larger velocities in velocity axis. But the overall tendency is not different from my work. So yeah, there could be an error, but actually we are working on how to measure the distance more correctly.
Excellent, thank you. Any other, one last?
3D distance, yeah, we measure the distance in 3D. Yeah, so it's, yeah, it's just a 3D distance from halo to the nearest filament points.
Okay, another question from Koranta. Last question.
It should be a quick question. Did you compute the distribution of the number of orbits?
Yeah, right. Yeah, I calculated it, and here you can see the effects. Sorry. Yeah, here yeah. Here, yeah, I calculated the number of orbits as a number of crossing moments. How many times it passes the way perpendicular 0 points.
Can you comment on how it goes with the number of orbits? Like, do you have no galaxies doing 3 or more, or like do you have very few?
Yeah, there are no 3 or the most the largest number of orbiting was the third 3, but there were really few. There were few. So.
Okay, if there are no further questions, I think we can stop for our coffee break. And so let's thank all of this morning's speakers.